Thank you.
Thanks so much, Deepa, for the introduction. And I'm equally honored that, I'm in the middle of faculty members, the technical people, some of the students may be there, as you said, who would be interested to listen to this. And I'll try and make it as interesting as possible in the next 1 hour time. And if you, Deepa, since I will be concentrating on the presentation, on the one, I will not be able to see if anybody raises their hand. Just stop me at any point because the questions asked are relevant at that point of instance, and that should be answered at that point of time if I may able to address it. Now, yeah, sure. Now, moving forward, before we go, I'm sure all of you will be quite upbeat about the green hydrogen because we are talking about hydrogen systems here. Green hydrogen is nothing but the source that it is using to obtain the hydrogen that's going to be utilized in the various systems. Now, green hydrogen obviously would be hydrogen which is being generated through the use of renewable, and here we are talking about the electrolysis process, and we would be taking into account the electrolyzer and the applications of a fuel cell, and also the various testing arrangements that is made while we are doing the while we are integrating the systems. Now, to start off, before I go into the nitty-gritties of the company I represent, just a moment. Let me just, Deepa, if you can confirm to see my screen with the four
Yeah, we are able
pictures.
to see yours.
Yes, we are able to see.
Great,
Yeah.
great. So let me move on to the slideshow. Good. You are able to see the full screen now?
Yes, perfect, perfect.
Wonderful. So if you see the picture at the bottom, that yellow, slightly yellow bordered picture, that's a fuel cell. Let me change the pointer. So this is a fuel cell. So this uses hydrogen and generates electrical current. So on the side, if you see, there is a vehicle here, and this is the fuel cell is placed here, and there is a hydrogen tank here. So in the uh, in the event that and it is running through a battery, so the batteries get charged by the electric current produced by this fuel cell, which is in turn getting charged by the hydrogen or from this tank. So this is what's going to be the future in case the battery operated cars are going to be using, instead of using a charging station, they can use it through an inbuilt fuel cell located inside the vehicle. Now these are used in most of the golf carts, which has been used in some of the golf courses across the country. Mainly, this has been the picture of this fuel cell is of BHEL, where we have helped them to develop the complete testing procedures, and we have certified the fuel cell. These are our sizes of 5 kilowatt. Now, if you see on this side of the picture, that this is a really big size fuel cell. This is about 125 kilowatt of two stacks of 125 kilowatt. So they would be fed by this hydrogen tank here, a bank of hydrogen cylinders. These hydrogen cylinders, they send the hydrogen into a common header. If you see this, there's a common header here, and from the header is located somewhere here, and then you have the pipeline, and the hydrogen goes inside this. Now, what you see here are the exhaust fans. So the importance of safety in the whole thing, this is under very controlled condition. We are checking the performance of this complete fuel cell system, and this complete fuel cell system, they are using a huge amount of hydrogen at a pressure of, say, around a pressure of 30 bar, and they are generating the electric current, which is going to be actually be charging the electrical motors. And this is for some project in the Middle East, which has been manufactured by one of the leading automotive manufacturer in global manufacturer. Now, if you see the whole scenario, so the whole fuel cell is under this container, and there is a lot of hydrogen bank here, and the hydrogen is transported here. Now, on the first night, I'm coming to this. Why I'm giving you this example and why I'm giving you this storyline is where you need the fuel cell. Where do you need the helium leak testing? Now, when we first started the testing about 3 years back, we pressurized the whole system. We purged the system through gas, then nitrogen, and then through hydrogen, and we sealed the system at 30 bar, and we left for the site and left for the hotel. And in the next 1 hour, we found that this pressure has dropped from 30 bar to 12 bar. And that was raising an alarm. And the alarm was, I mean, it was a visual perception that we saw the pressure falling down, but there was no alarm of the hydrogen getting picked up by the hydrogen sensor inside this fuel cell, because the airvac system was so well designed that the inside leakage was actually pushed out by the exhaust fans. So this is the second line of defense. So the question is, if the leakage is there and if you have a very good exhaust system, then you can avoid any sort of accidents to happen. So what we went back into in the morning, we shut down the systems, and then we tested it with normal air or with nitrogen, and we couldn't find the leakages. And then we started testing it with helium. So there was no helium leak test mechanic in this part of the Middle East. So we had to actually fly back to India and take the helium leak test equipment, go back there and test the helium leakages which happened through this. And you won't believe, 3 years back, we found there were almost 37 leakages in this one unit. And those 37 leakages, when we arrested them, when we changed the design of the joint, when we tightened the joints, till date there has not been a single leakage. And that's where which we when I say that, with a lot of emphasis, I say that helium leakage using 100% helium is the best thing that could happen in any hydrogen systems. So
Nilay, sorry, I had a quick input. I mean, can you share a little bit about what APAVE does specifically? And
yes. So now, and I just thought of giving this overview, so that now this is actually a
great. Sorry,
methanol refiner.
Normally people start with the company, their the people, the footprint and all. So sorry, please go ahead. Yeah, that was interesting start.
I normally spend not more than 10 seconds on these slides, because these may not be so important. It's important for me to showcase. So this is actually in the same site that you are seeing me. This is about 3 years back. Okay. And this is for a methanol reformer. The methanol is up here, and it's been done here. The methanol is converted into hydrogen. So APAVE is a global group which is available in almost 80 countries, close to 80 countries, and with a employee strength of 17,500, having a total turnover of 1.7 billion euro. So 1.7 billion euro means it's about 17,000 crores of the turnover which the group has. We are basically headquartered in, why I'm saying basically is it was very French centric. So it's a French company with almost 130 offices within France. Half of its turnover comes from France, and our major areas are process safety. One of the major area is training, giving training to develop electricians, forklift, asbestos safety, nuclear safety. So we have about roughly to the tune of, you can see we have 20 industrial test centers, and we have about 2,200 trainer inspectors. So we actually train roughly to the tune of 15,000 people in France every year. Now, having said that, the other streams which we are actually our core area is nuclear certification. So the plants, when they are being built, nuclear plants like the plants with EDF and the likes of other French giants, we help them to do the technical due diligence, we do the safety studies, and then we do the complete type approval of the major components which goes into the nuclear power plants. and the work doesn't finish, we can go up to the decommissioning of the plant when it happens. The other side, which is quite an interesting side, is we have got APAVE Aero Services. Now that comes under aeronautics, and APAVE Aero Services is like the DGQA, Director General of Civil Aviation, DGCA, the Director General of Civil Aviation in India. So any plane that lands of Air France, of course, or the French military, which takes off or which lands in France, has to be certified by us for airworthiness. So we have a strong team member of 600 people directly reporting to the French Ministry of Aviation, which does random checks on new built Airbus machines, Airbus 380s, all Airbus. So their airworthiness is decided. So we have a big bunch of design engineers, aeronautical engineers, which does that. Any of the Rafale flights which comes out of France is certified for airworthiness for us. Now you must be hearing a lot of Rafale jets being procured. So I can't say more than that, but it's definitely the prototypes will all be tested by us and will be certified by us, which will be made. We don't know how the thing will work out, but it's something that the Rafale organization will have to decide whether it is going to be only the prototype or moving forward in a large scale. So apart from these aero services and the nuclear, the other part is the training and the inspection services. So I belong to the inspection services in India, and I take care of the not only inspection services but also the non-destructive examination. That means wherever you have to do X-ray, gamma radiation, we have to use them for high thickness material welds, ultrasonic examinations of nuclear foundations. So all these things fall under the non-destructive examination, and that's a different vertical which is also available in India. So I think that gives you a fairly good idea about what we do and manage. In India, we mainly serve companies like Reliance for their shutdown inspections, for their buying their critical pressure vessels. We do a lot of crane inspections in China, which has been used by Adani's. When you go to the offshore side of ONGC, we certify their offshore platforms and their cross-country pipelines. So these are in a gist of what we do. I think I'll progress more than that. Let's stop about the organization there.
Yeah, sure.
Right.
Thanks a lot. That helped us. Yeah, thank you.
So the main, if you see that, the major areas are inspection, training, measure and test, and certify, and consulting and technical support. The entire hydrogen cycle is coming under the consulting and technical support. And these are the few areas which I have explained. So I'll not go infrastructure, transport, rail, and this is the aeronautical services. And you'll see the below the companies. All the high-speed railway in India, in Japan, in China are all certified by certifier, which is again a company by us. Hydrogen value expansion. So we have seen now that so many PLI schemes have been now approved by the government. So government has got the essential rules, the essential government's outlook on the green hydrogen production is very well defined. And what they are now doing, the entire government is now concentrating on running the pilot projects. So you will see a lot of 1 megawatt, 2 megawatt even plants have been built, except that now there is a 10,000 metric ton of green hydrogen production, which has been okayed by IOCL, which L&T is going to serve the entire lot of the electrolyzers. And now gradually the green hydrogen whole production is getting ramped up. Now green hydrogen also production is getting ramped up in the sense that they are going to use the green hydrogen either in the refineries. There are 3 areas. And the 3 areas of usage of green hydrogen is going to be transportation, is going to be in your steel manufacturing, in your refineries, and in the final one is in the fertilizer sector. So the 5 million metric tons, which is the government of India's vision to produce 5 million metric tons by 2030, is basically addressing these 4 areas. However, by 2030, this 5 million metric ton is going to go, and the increased requirement would be in the tune of another additional 7 million metric tons. So the production has to be to that level. Now, if there is going to be green ammonia, and if they're going to be producing hydrogen at one side and they're going to transport it to the other side, so transportation again is going to be a major area which is going to be a concern. A diverse hydrogen application, as we said, that it will be used for fuel cells. You can use it for the road transportation. You can use it for cars. You can use it for buses. Already there is a green hydrogen driven train which is designed in the north of India. And there are going to be hydrogen valleys which have been built. The leading one is built in Leh Ladakh by NTPC, and there is other one which is coming up in Andhra Pradesh. Now here you are seeing the actual pictures of the this particular electrolyzer. This is a 5 megawatt electrolyzer. This, if I stand here, my leg would be somewhere here and my head would be somewhere not on here. The head would be somewhere here. So you can imagine this is about 6.5 feet of diameter, and this length would be around 7 to 8 meters in length. And there are about 340 cells in this stacked up in this electrolyzer. This is a 5 megawatt electrolyzer, which means that it's going to be giving roughly to the tune of 1000 normalized meter cube of hydrogen per hour, which in turn comes to around 90 kg per hour. This is a full-fledged industrial application for electrolyzer. This is an electrolyzer plant, and this is a minuscule of this. Now, when you are developing, this is actually a lab in India. I can tell you this is one of the leading labs. They are now developing a lab which is going to generate 4 kg per hour of hydrogen. And this is one of the cells. So this is the cell they have developed. They have the electrolyzer been tested here, and we are involved in doing the complete safety study. What it means is we have to do the HAZOP study, the fire 3D modeling for fire explosion evaluation. We have to do the layout study where the hydrogen will be stored, where the lye will be stored, how the hydrogen leakages will be conducted. Then we have the emergency evacuation plan, and fire explosion evaluation is, of course, one of the major areas, and the quantitative risk assessment. So just to show the pictures of how it looks in a pilot phase, and these are the ones you can imagine for the IOCL. You would be needing about 25 or 30 of them, right, one after another. So you can imagine each generating about 90 kg of hydrogen per hour, which means if you have 10 such equipment, you will be producing 900 to 1 ton, almost 1 ton per hour of hydrogen. Why the leak testing matters in hydrogen? As I said, hydrogen leakage in its molecular stage, hydrogen is only detected very, very sensitively by using certain leak detection. And the leak detection is mainly, I've seen people using nitrogen gas, or even using 5% of hydrogen with nitrogen, and then they are passing it through the pipe, and then they're using a soap solution to do the leak testing. Mind you, we are talking about leakages to the power of 10 to the power minus 6, 10 to the power minus 9 cubic centimeter per second. Now, there is a very interesting fact that, if you see in your body, if you use a pacemaker, some of the people who use pacemakers are also tested with using helium leak test. And helium leak test, the allowable leakage, if there is somebody who says I can develop a system with zero leakage, then that's not correct. It's not humanly possible. There would be a leakage, which would be very minor. And the minor, in the sense 10 to the power minus 12 is the leakage allowed for your pacemaker. What it means is at 10 to the power minus 12 cubic centimeter per second, it means that if you keep 1 kg of helium in 1 liter of a volume of bottle, and if you allow 10 to the power minus 12 centimeter cubic centimeter per second leakage, it means it will take 15 years for that particular gas to come out of that completely. So it's a quantum of leakage that is a concern. So in hydrogen systems, we actually with APAVE systems, we do not allow more than 10 to the power minus 9 at the moment. So we are doing a lot of experimentations because there is not much data about the hydrogen explosions and the related accidents that has happened with respect to the new technologies which are coming up. But at the moment, we are demanding somewhere between 10 to the power minus 9 to 10 to the power minus 10 leakage rates, which are acceptable.
Um, uh, Nilay, can I ask a quick question, or shall we wait till the end?
No, sure.
I mean, normally we wait till the end, so I'll let Professor Jaya comment. But since you specifically said interrupt in between, I thought I'll just ask.
Absolutely.
Professor Jaya, let me know if we should wait till the end so that.
Deepa, you are the one moderating. Go ahead.
No. So, is there any? So, I mean, very interesting, especially the. You gave a very nice analogy that we could relate to in the pacemaker. So, is this only for pure hydrogen? The question I had is, or is it for the very, very explosive, perhaps even more than pure hydrogen or oxygen or hydrogen mixtures? I understand.
Of course.
They
Of
sort
course.
of.
Yeah.
And there was
Sorry.
and that question is very close to our heart because in about 5 years ago in ISC there was a major a very unfortunate incident. A life was lost, and it so happened after 3 months of study they've attributed with the world experts. Of course, they also, I don't know if they consulted with you, but they also had helium leak testing as part of the cylinders, and so on and so forth. So my question is it for hydrogen oxygen mixtures as well? And the second is, are there any statutes, that is regulatory standards that you will stipulate, or it's only based on preventive maintenance, and then as and when a Reliance or an Adani calls you, how does it work? Is there a particular world standard for this that
No.
uh-huh.
Okay, let me answer you that, this is a very pertinent questions. See, electrolyzers, uh, if you see the standard of ISO 22734, which talks about the stack and the system, they talk about limiting none of the systems they talk about helium leak test. Let me tell you that. Now,
I see.
these are our APAV systems. Now, but people believe it. People, when I speak to them, because it's if I talk about Middle East, it's very expensive. If you talk in India, we have at least 2 or 3 helium leak test facilities in every major city. I presume it is there. Now, the question is, what is safe? Now, here in the system, oxygen in hydrogen and hydrogen in oxygen, you rightly said, pure hydrogen is not having any problem. Pure hydrogen is, if you put a matchstick inside a pure hydrogen cylinder, it will not have any explosion. It's the mixture that causes an issue. So the 22734 very clearly says 2% of oxygen in hydrogen or 3% of hydrogen in oxygen. Either one of them, when the moment it overshoots that, the whole system shuts down. Now, so they are attacking the safety issues with respect to the mixture of that. They are not talking about the safety of the integrated pipelines. They are also saying that the LEL, 25% of the lower explosive limit is the one where you have to set your alarms. So the first alarm will go at 25%, the second alarm will go at 50%, and the third shutdown alarm is at 75% of the LEL. So that's the way they look at the system. Whether you are going to be using when you have the hydrogen and oxygen separator, when you go into the purification system of the electrolyzers, there are plenty of joints, there are plenty of loops through which the hydrogen moves into there. So there is no specific requirements.
Mhm.
They have to be leak proof, that they say.
Okay. Okay.
Now the question is again, leak proof is ideally they should be all have welded joints, but I'll show you some diagrams later on. Every joint cannot be welded. Specifically where you use fuel cell systems, you have so much of bends and turns, and at the last junction where the hydrogen goes into the fuel system, you have to have, the screw joints, so which are very susceptible for leakage. So you have to use very high standard of fittings, and what we are trying to do and help the industry is by saying is, instead of doing 100% helium leak test, can we do a mixture of 20% helium and 80% air or nitrogen? Now that is an experimentation which is right now been done. We have come up to 30% or 35%, but below a certain limit, the tests are not effective.
Okay. Okay.
I
Sure.
mean, does it answer your question?
Yes. Yes. I mean, that gave a lot of, because clarity to the, I mean, just to highlight, hydrogen per se is not, it's the combination is deadly. So even a very
Yes.
small percentage. So
Uh, I was with the Indian government, which is the PESO,
Mm.
the explosives department. So I
Uh-huh.
was recently in Hyderabad. In fact, from that place, when we last met, I was actually flying into Hyderabad to do the Type 3 cylinder testing for hydrogen.
I
And
see.
Type 3 is a combination of a metal and a FRP lining on top. And a
Mhm.
Type 4 cylinder is nothing but a totally carbon fiber cylinder.
Mhm.
Now, we are talking about pressures in the range of 900 to 1200 bar.
Oh, wow. Okay.
So for 900 to 1200 bar pressure, the thickness of material, a stainless steel cylinder, or the weight of the stainless steel cylinder vis-a-vis the weight of a carbon fiber cylinder, you will have a weight reduction of about 60%.
Mhm.
So you
Right.
can imagine, how much of more weight you can carry in the same container truck when you're going to transfer hydrogen, and what would be
Mhm.
the weight. So these are much more alternatives which are coming out. Still, the PESO has not really approved Type 4 cylinders to be used in India. But
Okay.
this one, I was discussing with them, and I was actually pushing hard. Maybe sooner or later, I will discuss with them to give them a overview of what we are giving it to you actually,
Oh, nice.
and
Maybe
try to
there's
say that
somebody here. I can see some people here are from Government of India. They may make a note of it. Yeah. Yeah. Thanks, Nilay. Please proceed.
Yeah.
Yeah, please go ahead.
So this is actually a picture of which I normally don't want to show, but today I'm showing it because we're addressing a lot of people here. This is 2023. One is in California, and the other one is somewhere in, I think, in Netherlands. And both, you see the bus on the right hand side and the picture on the left hand side. This is actually a hydrogen cylinder driven bus. So it's a
Mhm.
hydrogen bus. And ultimately, what has happened, they were using Type 4 cylinders. That's why I was just telling you that this Type 4 cylinders are used quite rampantly across the globe. And unfortunately, both the buses had been using the same Type 4 cylinders, and the same company which did the technology driven into both of them. And what it happened was, basically they found that one of the errors in tightening one of the fittings in the buses led to the accumulation, leakage and accumulation of the hydrogen inside the bus, and it caught fire. So these sort of accidents, you will never come to know the truth behind it because of the political reasons, or the country doesn't want to come out with the truth things. But this is what has been purported as the main culprit, the o-ring of a valve which caused the faulty o-ring, and it caused a leakage. It can be true also, but this is a very hard reality to show that, we if we are going to use hydrogen in a bus, you can imagine the bus has got so many passengers, and if the hydrogen is going to be, the hydrogen has got a very pooling, the hydrogen pooling property of hydrogen is very, very strange, and it has got different pulling properties on gravel, on sandy area. So I'm not going into that, but these are stark reality of what can happen if there is a leakage inside, and you have the mixture of air with that. So this is again something which we have were showing you that uh, gas permeability. This type 4 cylinders, which is made of carbon fiber, and if you can see the construction of the cylinder I've shown here, it has got no metal inside. It's got layers of carbon fiber, and it's basically a high molecular polymer lining. These cylinders, the specification, if you go to the specification, which is ISO 11119-3, is the international specification. It allows a certain quantity of gas, hydrogen gas, to permeate through the walls of this cylinder. Quite scary, right?
Mhm.
Now, then again, if you see the leakage rates are in so much of 10 to the power minus so much that hardly should be bothered. Now, the only way we can do that is keeping pressurizing the hydrogen inside the cylinders and keeping the entire cylinder under a vacuum chamber where you actually dip a sniffer and see over an extended period of time, is there any leakage which is coming out. Now, imagine these cylinders were used in these buses, and if that permeability has been compromised, then you can imagine the hydrogen without coming out from the valves at the corners, on these corners, even with no leakage, it can still permeate it through the walls and would have caused that. And none of the conventional non-destructive testing of ultrasonic testing, radiography testing, PT examination, that is penetrant testing, dye penetration, or magnetic particle testing, or an hydro test could cross, detect that leakage. It's the only helium leak test. Some hydrogen demands of why we have the advanced entity. Hydrogen being the smallest molecule size with 0.29 nanometers, high diffusibility, low ignition energy. And mind you, when you have a hydrogen fire, you cannot see the hydrogen fire. It's colorless. And we actually install in a lot of areas to pick up the hydrogen fire. We have put up infrared cameras to pick up the hydrogen fires. And of course, in carbon steel, in low alloy steel, we have the intensification of crack initiation and growth mechanisms by which hydrogen and delayed cracking that can happen. This hydrogen induced material degradation. It's a subject on its own, and I don't want to touch that now because that's going to be again a material science which can be dealt in any other on a separate date. So just wanted to give you an overview of why the demand. Why that hydrogen demands advanced entity. So what happened? How the evolution of the helium leak testing. 1980, helium leak testing introduced for safety critical applications. 1990, the first fuel cell and electrolyzer R&D they performed. The adoption was done, and then the standardization for the protocols for SOFC and PEM type electrolyzers stack manufacturing was done. Expanded in 2010, expanded use in the hydrogen production, storage, and distribution equipment. And in 2020 is the emergency of the gold standard for hydrogen leak certification in hydrogen systems. Now helium leak test we have been doing. I remember we have done plenty of butterfly valves for the Indian nuclear industry. So in nuclear industry, it is well driven. 10 to the power minus 9 cubic centimeters per second. Anything to go into the nuclear side of the plant will has to be helium leak tested.
I would imagine it to be very popular also in the space, right? Because a lot of the
Very much.
cryogenic and a lot of the systems use hydrogen, even though it may not be green, but they need it. So do you also serve the space industry quite a bit?
In France, we do it. We
Okay.
have a complete space department. We have hydrogen. We have very highly sensitive helium leak test equipments in India, and we do it for very critical heat exchangers. We insert those helium leak test detection tubes into the heat exchanger tubes, because in tubes, if you have a leakage, then the whole plant performance comes down. And there
Yes.
we are using the helium leak test. So we have got a couple of very sensitive equipments in India, which is used in most of the clients' area.
Sure.
It's an expensive test.
Right.
So
Okay.
here you can see the electrolyzer, and this is the balance of plant. So in the balance of plant, you have the hydrogen and oxygen separator, and then from here it goes into the purification columns, and then the hydrogen is coming out from somewhere. The hydrogen will be let off for the use, further use. Now you can imagine all these 300 or 400 cells here. Each of them are prone for leakage, and it's advised that a helium leak test is done by pressurizing the system through helium leak and then using a sniffer to come across. Now, these are very important at this stage, because this is a new technology as far as India is concerned, where you are going to ramp up. Now, if you need 10,000 tons of green hydrogen, then you can imagine the big electrolyzer which I shown. You would need about 10, about 100 of them. So if 100 of them has, each one of them has some leakages from somewhere, you can imagine that that whole plant will be like an acting bomb, unless you have a very good system by which the air is excavated out of that plant. So the balance of plant has got a lot of leakage points. Electrolyzer system itself has got some leakage points here. Now this is where you can see the hydrogen. Let me go to the next one with the electrolyzer. So here is the electrolyzer. We have the water coming in from here, and we have the hydrogen coming out in this location, and you have the oxygen in this part. If I go back to this, these are the two containers which are shown here, these two, and then the hydrogen is passed through various cylinders which purifies it. It goes through a volute, and it has got certain absorbers which takes away the water, and you ultimately get, if you need it for an ammonia application, then you need 99.99% pure hydrogen to be utilized through for the application. And this one is, if I go back again on top, these are the cylinders which are represented here. And the oxygen is either vented out, or you can further use it based on the quantification of the oxygen. A lot of people can use this oxygen for your medical applications. So you can imagine one cell has got so much components, and each 5 megawatt electrolyzer would have about 350 such cells. So you can see the total number of joints in each cell which can happen. I'll not spend much time on this. So
sorry, quick question on the previous page. So this whole thing is sort of, you hermetically seal it in each of the cells is hermetically sealed in something, or when you
just
said
with
you had
O-rings, this with
just with
O-rings,
O-rings. Okay.
and if you see these tie rods, they
Mm-hmm.
go through them.
Okay.
They go through. So basically, these are the two extreme end bipolar plates are the
Yes.
extreme ends, and then
Mm-hmm.
these bottom ones are very, very thin layers which gets encapsulated within the bipolar plates.
Mm-hmm.
And these end these are the what do you call, the pressure plates which actually compresses the entire cells together, and they are highly tightened. These are spring loaded gaskets. They're spring loaded washers.
Okay. So the leak, basically the leak is at anywhere there is a joint, there's an O-ring which is some
So
form of rubber.
yes, anywhere from these joints, the leak can happen.
Okay.
Ultimately, there can be, see, these leakages from this particular one, these three plates may not result in a leakage outside. The leakage outside will happen only where this O-ring is been clubbed with this particular biplate.
Okay.
So there is one joint every cell where the leakage can happen. So you have to actually take a sniffer and go all around very slowly to understand if there's a leakage or not.
And
So
then you, I mean, they, of course, you will tell them these are the locations, and then they have to figure out how will you do a kappa, like
yes,
a corrective action and the preventive action to, I mean,
exactly.
that's not your scope, right? You will only give them the,
That's
huh,
yeah, correct.
okay,
So
okay.
basically, so if we have to go a little bit backward in order for us to have a leak-proof joint. The O-ring sitting area has to be having a certain micro finish. The dimensions should be such that, and then you have to ensure that this tightening of these bolts are also done in a particular sequence. These are all very scientifically done, so that because after you assemble all the cells together, and if you have 5 cells in between which are leaking, you actually have to dismantle the entire stuff.
Mm, true.
So and there has been now accidents, there has been deaths in India,
Oh,
in China through
I see.
this, and it's a very common problem
Mm-hmm.
because, mind you, the temperatures in these areas are the tune of the ideally when they work, they should not exceed 70 degrees centigrade, but then you will have local hotspots, and that's where the engineering comes.
Mm-hmm.
So our organization has the capacity to actually study the computational fluid dynamic studies which has been done, and tell you that whether these studies will help you in a laminar flow and going to be creating some hotspots or not.
Okay. Thank you.
So I'll not do much of this. There is a huge limitation of a hydro test, because people might say I will do an hydro test and see if there is any leakage there or not. This is simply not possible. And why it is not possible, it's been given here.
Mm-hmm.
Now, you can see by doing a bubble test, you can only create hardly any what you call uh, leakage which can happen. With hydrostatic testing, still there is a big gap which is opened up. But with a helium leak test, you can absolutely create a zero leakage path. You can absolutely trap all the leakages which can happen there.
Mm-hmm. Yes.
So this is a picture which I wanted to show, that this is a fuel cell, uh, and you can see that this is the fuel cell rack, and below these are the pipelines through which the hydrogen travels, and you can see the number of joints here. So each and every joint, when we test, we wrap them up with a black tape like this, which is impervious, and then we run the helium through these pipes. And in each of these joints, what we do is we actually have a sniffer, a small sniffer and a pointer, which we push it like a injection. We push the tip of the probe into this joint in through this particular tape. This is the black tape, a very high quality black tape, and then we measure the hydrogen leakage inside this. And you have to be an expert. Basically, the moment you insert that, the value will show high, and then the helium will leak through the leakages. You will not get that value. So again, if there is a spike of value here, you will have to again tape it up, give it some time for the leakage to accumulate, and then again do the testing. And as we were saying, when this is an actual testing that we have taken the pictures, and during this testing, we saw out of almost 75 joints, almost 37 joints were leaking initially.
Oh, okay.
So these are something which I will share this topic uh, it can be which method of helium leak test you are using. So global helium vacuum test means if I the sniffer method is just what I showed you. You have to insert a sniffer into these joints here through this tape and measure it. If I go for the global helium vacuum test, then what it happens is in a global leakage test, this whole cylinder is first filled with helium leak test, helium gas at a pressure, and then instead of sniffing it around everywhere, and there's a possibility that you may miss out the sniff, we place the cylinder, seal the cylinder, and place it inside a vacuum chamber. And on top of the vacuum chamber, we just insert the sniffer. So any leakage from here will be coming into the vacuum, and the sniffer will pick it up very easily. So for very critical application, we actually deliver this global helium vacuum test.
I see. I see.
So these are the permissible helium. These are uh, our own acceptable limits, which we have done through our engineering studies and our experience. And this can be shared. But you can't come out and tell me that, you can challenge, and we will be very happy to see why the challenge is made and what has made you to challenge these values.
Mhm.
I'll share this presentation later on.
Wow, that'll be great.
Yeah, please. So if you see here, the case results and the impact and the outcomes, which are technical outcomes. If you see the leak detectability, observation before helium leak test, observation after helium leak test, and technical impact. Now, for all these ones, if you see the fuel cell stack life, which is 4,500 hours of operating hours, observation after helium leak test is 6,200 operating normal. Before helium leak test was applied, they were not shutting down before 4,500 operating hours. After helium leak test, they could operate up to 6,200 operating hours. That means it is an improvement of 38% of durability. And operation downtime is frequent leak-based alarms causing shutdowns, which is normally without helium leak test. Zero unplanned shutdowns over 10,000 hours. This is something which is very, very important.
Mhm.
Improved availability and uptime. So manufacturing rework, if you ask without leak test, it's almost 25 to 30% of the assemblies sent for rework. When you said that something is leaking after we are doing the testing, now once you do the commissioning, then these problems arise, and you send almost 30% of the assemblies are sent for retightening, rechecking for the leakages. But this is reduced by almost 40% if you are doing a helium leak test at the factory site. In process safety performance, two major hydrogen accumulation events recorded with 1%. This is very important. We tried with 1% helium leak test. That means 99% of nitrogen, 1% helium. And we had two major hydrogen accumulation events. That means in two major cases, hydrogen was found to be accumulated. And 9 major leaks with 25% and 27 major leaks were detected 100% of the helium leak test, and in the same setup. So this is an experimentation that we have done. So, the number which I was saying 37 was not correct. It is 27. 27 major leakages were found with helium with 100% helium leak test. But how much is the repeatability? That has to be checked like this. Zero events with 100% helium leak test. And with this, actually, you can actually completely mitigate the explosive atmosphere risk.
If I may ask a question here, Nilay, you're talking
Yeah.
about I mean, when you say observation after helium leak test, you also you're saying or implying that after the leak test, things have been fixed, and therefore this has come down. Is that what it is meaning?
Correct. So
Okay.
once if I go into the operation downtime, that means you do not
Yeah.
have any unplanned shutdowns for 10,000 hours. If there are planned shutdowns, it has to be done. Planned shutdowns will have to be done, but unplanned, nothing before 10,000 hours.
Yeah. Thanks.
So
I had a quick question on that as well. So these are preventive maintenance, is it? When you talk of the unplanned shutdowns, or is it
yes,
during an
the planned
so
shutdowns are preventive maintenance.
okay. And what about the fuel stack life? What you're talking about is also before installing the stock or a stack, or is it during an L1 or something like that?
During an L1.
During an L1, okay.
Yeah.
Because the whole thing, so once you do it, then they will do some corrective measures or replace
Exactly.
defective O-rings or whatever.
Absolutely.
And then the clock starts after that, right?
Yes.
Okay, okay. Sure. And another quick question is, are you also, I mean, does APAVE also make these equipment, or
No,
you
no,
are
no,
only
no.
the, I mean, you're sort
We
of like the third party inspection?
Yes, we have our own equipment. So if
Okay.
so, as I said, we have an NDT team, which there's about 300 people. The NDT is one of our major work across the globe.
Okay. I see.
So
I see.
right from doing infrared crack detection on windmills, on windmills, these wind towers, they have, each blade is about 120 meters. So you can imagine the size of the windmill.
Yes.
So how do you do the corrosion mapping on those? How do you do the leak testing of those? Not crack detection of those in-service blades of the
Mm-hmm.
wind turbines. That's another specialty which we have developed in the US.
Oh, nice, nice. Yeah, that's not trivial because
Yeah,
we've
I mean,
seen.
that's really high tech.
Yeah, yeah, correct. I thought they were also trying to do that with all kinds of fancy drones. You know,
If I have time, then I can actually find out that, and I can show you a small presentation if I have time. But let me finish this off.
sure, sure.
So barriers for NDT adoption, hydrogen and critical energy system. This is cost sensitive, definitely cost sensitive, and that's the biggest barrier. The second thing is a skill and competencies gap. The skill and the competency gap is not for the people who are doing the testing, but in the actual application where you have in the manufacturer's premises or in the projects. Infrastructure limitations, you do not have a proper leak detection system. And of course, the last one, which is the least one, is actually the standard or code ambiguity. So, I always say that you have a triangle, and each part of the triangle is one apex part is cost and quality and time. So you cannot have all three together. If you want to give a lot of, if you want fast and if you want them cheap, you can't have quality. If you want to have cheap and if you want to have quality, you cannot have it fast. So like this.
Mhm.
And that's all for my session here. I keep it open for in case.
Yeah, thank you. Thank you so much. I mean, I could listen to several hours of this at least. So it's quite fascinating for me from a practical application. So I think the floor is open to any questions or comments. Yes, from the audience.
If people could raise their hands, then I can call them out one by one. Professor Rasi Prasad. Yeah, you can go ahead, Professor Prasad.
If you may want, please unmute yourself, Professor Prasad. Please go ahead and ask the questions.
I'm not sure why he's. I mean, I'm also not able to unmute him from my side.
Let me say, even I can't unmute.
Can you hear me now?
Yeah.
Yes, yes.
Okay, so this can be used for any leak testing, not necessarily being hydrogen. Anything which has got a perforation or starts, gives a leakage, it can be tested. Of course, hydrogen, these fuel cells being very important area. Now you use three methods for this testing. One is you apply this gas from outside or inside, or you use so like a vacuum chamber or something like that, which you call bombing or something like that. So in all these cases, it is very difficult for many complicated. You cannot have a handhold analyzer and go and test this leakage. So in those conditions, you need to have a system which is already integrated in the manufacturing itself. Otherwise, it will be very difficult for a complicated system, to go and analyze that, So, because for simple tests, it's fine. Like you said, these cylinders, which are made of your steel, now they are for cylinders that they are using composites also. But there also there is a problem. Like, this helium may react with, say, plastics, and there may be certain issues related to that, which people are not very much aware of. So
Sure.
those precautions also need some attention, like that. And third thing is you
Good
just
point.
find out, that we need a location, pinpointed location, and we also need to monitor that how this is growing, so that you can do a not reactive but a preventive maintenance. Like I will wait for this time, this much of time. I can tolerate that. So how is that all taken care of?
So if you see, first of all, very good question actually, because a lot of places they don't. I was asking one of the automobile. I'm not naming them right now. So I was asking one leading truck manufacturers in India, and I was telling them that how are you going to, in if you're using your hydrogen systems in the truck and it starts leaking, how do you manage to stop and measure and then come out? The hydrogen may not be picked up sometimes inside the closed environment, and it's hot. So they have developed certain system by which the when you have a detection, when you have a hydrogen leakage, the obviously the flow of hydrogen in terms of 0.00001 10 to the minus 6 changes in flow can happen. And by detecting these changes in flow, they actually keep a shutdown. So they don't have a active mechanism to measure the leakage. They have a passive mechanism through which the leakages can be. They will ascertain, the system will ascertain that there is a leakage which is happening in the system in the one of the places in the loop, and they will shut down. So that's the first part which you were saying, and I really like that the inference that you made on that. Now, can you come back on the second question of it?
No, exact location and the growth of that, because if suppose it is developing, right? Let us take one example. So we can find out the pit growth rate. So similarly, is there anything that leakage, intensity is increasing, and therefore there is a threshold which we can tolerate, and beyond that, we can say, okay, fine, go and change it.
So all these leakages, which I was saying, 27. So if the leakage rate is actually picked up by that equipment, let me just share it with you right now. Let me show it to you. Can you see this machine here?
Yeah.
So this machine will tell you the amount of leakage which is picked up by the sniffer. Now, if this leakage rate is beyond your acceptable limit of 10 to the power minus 6 or 10 to the power minus 9 cubic centimeter per second, you'll have to calculate that, of course. And then if that is the case, then you know that this is the leakage which is going to happen from there and it's not acceptable.
Sir, it is a very small area. We are referring to a SCADA systems,
Sorry, I lost him.
And now government is planning, with natural gas, they are trying to add some part of hydrogen and things like that. So if you want to have the integrity of those systems, you have to tell pinpointedly that what is the location where this damage is being done. And, then only, you can take corrective action. So how can you integrate this in a SCADA system so that, you get alarm, or is it done like that?
You can use a hydrogen leak detection system, helium leak detection system through SCADA when the whole equipment is running. And what happens is, that's what I was saying, that one of the automotive manufacturers, what they found out is when the hydrogen flow is happening, if there is a leakage, the flow of the hydrogen will change. I'm talking about the flow in terms of 0.000001. So the SCADA system will detect the change of flow of hydrogen within that pipeline. And these are very thin pipelines and very sensitive pipelines like these. And when they detect that changes in the hydrogen flow, because there is a leakage, the flow will reduce. Because of the reduction, the whole system will set up an alarm.
What about the buried pipelines? Can it detect?
Yeah, of course, the same principle.
Okay, thank you.
There are a lot of systems which are developed now on detecting detecting cracks through eddy current, through helium leak test, and by measuring the flow. It has to be sensitive. Now, if you're talking about an underground pipeline, what is the size of pipeline you're talking about? Can you tell me?
Transmission pipelines, large dia. So it can be used for both transmission as well as distribution pipelines, you see.
Correct. Large diameter pipelines, what are they carrying? Gas, of course, right?
Of course, gas, and as well as now there's a mixing of blending of hydrogen,
Correct. So this is the major challenge. If you're blending 20%, the blending is not happening beyond 20%. Am I correct by saying that, or you have got
Yeah. So far, that is the scenario.
So that is the scenario. So the challenge is, these are all carbon steel piping where you are using gas, which can be easily detected by a bubble test. That means when the gas is passing, I have checked myself, when on all the joints, you can use a soap solution which can detect the bubbles. But hydrogen will not have a bubble. With normal soap solution, you cannot find out that hydrogen bubbling out from there. You have special bubble creating solutions. Now, if you use those bubble creating solutions in those large diameter pipelines, you will detect those hydrogen cracks. But they are very expensive.
Actually, you are situated in Mumbai, Navi Mumbai, isn't it? So I'm also in Mumbai. So I would like to have some more in-depth information from you. So can you send your email address?
I'll put it in the.
Yeah, that will be nice.
I'll put.
Okay, thank you.
Welcome, most welcome. I'll put it in the chat box for anybody to do it.
Okay, thank you.
And in fact, I can help you out in those pipelines, because we do a lot of cross-country pipeline for Oil India, ONGC.
I mean, these are, just to take on this dialogue. So these are things which the pigs, I mean, the resolution of this is sub-micron or something like that, right? Which the pigs cannot do. Okay. And I'll just take one point that Professor Prasad made, which you also made in your second or third slide, which is in passing. If you're running out of time, I can ask you later. But basically, the interaction of these with, we're very preoccupied with, especially in the nuclear that you mentioned, how these interact, the detection or the NDT technique itself, its interaction with the material of construction. You also made a point. Professor Prasad also made a point there. So is that anything of concern? I mean, sending these into a system, is it going to cause more embrittlement just because you're using an inspection technique? You made something in passing. I just thought I'll ask that.
But in the nuclear, this is basically Section 5, Article 10 clearly defines the norms that has to be used. The NPCIL has got very clear acceptable norms and at what applications you're going to use them. I was not actually aware of the plastics been getting affected by helium, as Mr. Prasad was mentioning. That's a very good point, actually, which I'll deep dive, because in the butterfly valves you have rubber nitrile liners which are used and on which the whole valve rotates. So under those circumstances, NPCIL guidelines very clearly says that you have to do the sniffer test, and we have done about hundreds of them. So, but it's a good point. I will keep that as a cursory note now, because we have to go into the MSDS of that particular lining material and ensure that it is not reactive. Because similar things I have faced even for hydrogen services. In certain linings inside the equipment is such that it reacts with the water, and the water test cannot be used because the code doesn't allow you to do a pneumatic test in lieu of the hydro test. So if you are going to use a pneumatic test in lieu of the hydro test, then you have to have a solid foundation and technical justification, which comes to us, and then we let them go for a pneumatic testing.
And you use it for your hermetically sealed semiconductor devices also?
Yes.
So are you in practical, are you giving some sort of a thing? Because how will you detect that whether it is in a transistor, diode, or any other component, because it consists of so many components.
Correct. So I will not be able to answer you directly on that, but this address is done by our different instrumentation group, and they can tell you.
But ASTM standard F239, that gives some specific standard for this?
I'm not able to say that, sir.
Okay.
I am talking about ASME section 5, article 10, which refers to all the helium detection mechanisms.
This ASTM F239 is a specific pass-fail criteria,
Okay.
So anyway, thank you so much. I will meet you sometimes in Navi Mumbai.
Sure. Prakash ji has got some raised hand.
Yeah, good evening and thank you for nice talk. Of course, my name is Prakash Ghosh. I'm calling from IIT Bombay. So I think you are mentioning 30 bar in fuel cell. Mostly fuel cell operating pressure is below 1 bar gauge. Mostly it's 0.4 bar to 0.9 bar. That's the operating pressure if you take the gauge pressure. So why do we need 30 bar there? That was my first question. Second question, in case of electrolyzer, generally electrolyzer is flooded with KOH water if you take alkaline. So in that case, even if you put helium, actually helium is not going to reach inside your electrolyzer, it will be in the pipe because it's completely flooded. So how is it going to help in case of, because you are showing that O-ring, through that O-ring ultimately is the KOH which is going to push the pressure. So that's the second question, that how it helps doing that helium test in alkaline electrolyzer when alkaline electrolyzer itself completely flooded. Number 3 is that helium, of course, you are going to get safer because helium is even smaller than hydrogen. But aren't we also, you were talking about the costing. And because this particular, all this technology becoming more expensive because we are putting this type of hydrogen phobia, telling hydrogen is very dangerous. Because I will be telling this one, when you are talking about 10 to the minus centimeter cube per second, in that pipe you are talking about, there you will be having 500 LPM is that the total hydrogen flow rate. So if you take that total flow rate and with that percentage you are telling how much is leakage is actually negligibly zero. Why will we bother about that much in that case if it is not causing too much of, let's say, cost? Because when you are talking about this leakage, one is your safety, other one is that cost. So, and then if you tell this much of hydrogen is coming out from your that pressure, and then when it comes out again because of the hydrogen diffusivity, it comes out in the air, it becomes completely diluted. It actually goes below 4% very easily. So why will we bother so much about this type of leakage and then putting that hydrogen phobia in the mind of the people?
Okay, I'll answer to your second part first. See, what has happened is here, India is just gradually developing the electrolyzer systems in India. So far, when you import a stack from, say, China or from Germany, and especially for the lower cost stacks, when they come, we have got at least 10 examples where the stack has, one of the cells have burst, the O-ring has given way, and what you have to do is you have to shut the plant for at least 2 months, send the whole stack, open the whole stack and send it across to the country where it has come from, and they will replace it again. So can you imagine the amount of loss that has happened? Now, in order, what we are mentioning is you should not, if I go back to what I was mentioning, the importance of the helium leak test is in the initial development of your process parameters, where the O-ring is sitting. Now, once you have a very established process developed that on the bipolar plate, this is where my O-ring is sitting, this is my O-ring dimension, this is the groove dimension, this is the surface finish, and if I use this amount of torque to tighten it and keep it too much, not too much torque, not too less, those process parameters are to be set in such a way. To arrive at those process parameters, you need to test your systems so well. Otherwise, you will land up getting leakage things which will make your OPEX price go up. Shutdowns will be tremendous. So hydrogen is not a difficult gas to deal with. You're dealing with hydrogen for a long time, for decades, for centuries actually. But the question is about, I'm not concerned about the balance of plant. I'm concerned about the stack. So the stack, if you can you repair the stack in situ in any of the commission plants? My question to you.
No, my question is that when that stack is completely flooded with your KOH water, how putting helium is going to help? Because anyway, if you are putting helium
No,
in that,
not that time. No, not that time. We are doing the helium leak test during the manufacturing of the stack at the initial stage for pressure, just passing the helium leak through the cells, through the
no,
hydrogen
I got
line.
that point. My question is different. I'm telling that when you are going to use the stack in real practice, you are not going to use any gas inside. You are going to use a KOH flooded, and you are
Correct.
going almost at 10 to the power 5, let's say -9, that leakage rate with helium. Then afterwards, when actual operation comes, it becomes your KOH or water. So you don't need that much of leak proof in case of actual electrolyzer when it is flooded with KOH. This is my opinion.
Uh, you are to a certain extent correct, but can you imagine the interface where the hydrogen is gets coming out into this separator line?
Yes, sir. Let me tell you. Okay, just to give my background, I did my PhD in Germany from 99. I'm working with hydrogen. I made my fuel cell in 2002, or 5 kilowatt stack, what you are saying. Now we are making in India. You also, I'll invite you to come into IIT Bombay. We test our own electrolyzer we have made, Indian made, not we take from anywhere. And we also put fire on hydrogen, and we use hydrogen for cooking. So then lots of the things what is being discussed as a hydrogen, I also read all those things. I feel that, okay, this is creating lots of phobia among the people when you talk about hydrogen, because even we're telling we allow hydrogen to come out from our burner at a rate of 10 LPM to 100 LPM, and we put a small burner to big burner. So that's my question, because when we are talking all these things, let's say the one is that the loss you told is that how much flow rate it is going in the fuel cell stack and how much percentage of that is leaking, that is negligibly zero. That's what I was telling. If you take 120 kilowatt of stack, that will be requiring approximately 250 to 500 LPM of your hydrogen flow. Now in that, if you have 10 to the minus centimeter cube, that means 10 to the minus ml of per second, it is negligibly zero in terms of, that means the total life cycle costing will be also negligibly zero, and also the safety hazard because of this leakage will be also negligibly zero.
Prakashji, I want to stop you here in the sense that we wanted to not create a zero leakage, which I said is not possible, but these standards have been followed to ensure that we minimize the risk to almost, near zero allowed regions. So in order for us to ensure that the leakages in that minor part also is to be taken care of, we are putting the so strict numbers. Otherwise, what will happen is if you allow lower limits to be happening, people will try to abuse it. So it is not
Also-
about hybrid. Yeah, sorry. Please,
No, sorry,
Deepaji.
please go ahead. No, I wanted to just answer Professor Prakash, of course, that the question that I also asked, no, it's more of the hydrogen oxygen mixture, as you know very well, sir. That is extremely dangerous. Hydrogen by yourself, you're right. We all burn. Mr. Nilay also clarified that at the beginning. I think not everybody is aware of this deadly combination. A lot of hazard. I mean, there have been some enormous, terrible, fatal accidents in this range of mixture. So uh, I think probably what Nilay also right at the beginning suggested was the examples he gave in the Netherlands and the California hydrogen bus accidents. I think that is the essence of this detection, not in your electrolytic cell itself. It's in the outside that the combination that we are trying to look for in all these plants.
Very well stated, absolutely.
It's a sort of a Z-shaped curve, right?
Because
Mhm.
yes, Deepa, you are right, because this liquid hydrogen and oxygen, is
Yeah.
used
It's quite deadly,
in our
actually. I
research for
mean,
the third stage
not
rockets.
many. Yeah,
And that is how it
and
fires.
really
It
not
fires the
many
engines.
people. Yeah, sorry, it's
Electrolyzer.
very, very dangerous, not hydrogen by itself. And not many even big gas companies in India, if you read some of the recent explosions that took place, people are not even aware, people who are doing the bottling. I'm not saying in specific names, big names, but including that, they're not even aware. And it's even we are not aware. We just use it in the lab sometimes. Only recently it has come into the picture, and I think that's where the technique that he's telling is extremely potent. It is expensive, absolutely. He said that in every slide, but I think anyway, it's 7:30 now. It looks like, Nilay, it's such an interesting talk that, with experts also online, we could go on forever, but I think Professor Jaya she will remind us that we are due, we usually keep to time, so.
No, I just would like to just stop the recording. That's all, because the file size will then become too big for me to store.
Yeah, true.
But
But
yeah, that's one of the.
no, I really